In just 1 month, the University of Chicago has quietly delivered the quantum computing world two separate breakthroughs that researchers have been hunting for years. Not one discovery, two. And hardly anyone outside a tight circle of physicists has caught on to just how significant this really is. If you've been tracking the quantum computing race, you already know the whole field is fixated on one brutal challenge. The math becomes so tangled so quickly that even the world's most powerful supercomputers can't handle it. Now, a single university planted in the middle of the American Midwest has come up with not one, but two clever ways to slice through that complexity, both within the same 30-day stretch. Stay with us, because by the end of this video, you'll understand exactly why scientists are calling this one of the most productive stretches in recent quantum history. Let's begin with the first shortcut, since it's the one stirring up the most excitement inside the physics community. Researchers at the University of Chicago stumbled onto a surprisingly straightforward way to create powerful quantum states that have historically been a nightmare to produce. Here's the part that should catch you off guard. They didn't need to construct any new exotic equipment. They didn't need a bigger, pricier machine. All they did was make small, precise tweaks to the energy levels of atoms sitting inside something called an optical cavity. That's the whole trick. With those minor adjustments, the team managed to generate a wide range of highly entangled quantum states, the very kind that future quantum sensors and quantum computers rely on to operate. If this sounds almost too easy to be true for something this important, you're reacting exactly the way the rest of the physics world did. Hit that like button right now, because what comes next explains why this matters so much. To grasp why this is such a major deal, you need to understand entanglement itself, since it's the secret ingredient behind nearly every advanced quantum technology being developed today. Entanglement is the bizarre phenomenon where two or more particles become so tightly linked that whatever happens to one instantly affects the other, regardless of distance. Einstein famously labeled this spooky action at a distance because it appeared to violate the rules of classical physics as we knew them. For decades, producing these entangled states in a lab has demanded incredibly sophisticated equipment and meticulously engineered setups, the kind of resources only a handful of elite labs worldwide can afford. The University of Chicago team, operating out of the Pritzker School of Molecular Engineering, found a way to bypass all of that complexity. Rather than blasting atoms with new lasers or installing brand new hardware, they simply shifted the excited state energies of specific atom pairs, giving each pair an equal but opposite energy offset. That subtle shift alone was enough to produce complex entangled states using equipment many labs already have on hand. Don't forget to subscribe, because what this team uncovered next ties directly into a second breakthrough. Now here's where the story really gets interesting, because this wasn't an isolated event. In that very same month, an entirely different challenge within quantum computing got its own shortcut. And this one tackles a problem that has frustrated physicists for years, the nightmare of simulating quantum phase transitions. If you've never heard that term, think of it this way. You already understand phase transitions from everyday life. Water boils into steam, ice melts into liquid. Those are phase transitions you can see and feel. But there's a far stranger, far tougher version of this phenomenon that occurs at the quantum level when certain materials are cooled to nearly absolute zero. At that point, a material can flip from magnetic to non-magnetic, or suddenly gain the almost superhero-like ability to conduct electricity without losing any energy as heat. The math required to simulate these transitions is so demanding, it can overwhelm even today's most powerful supercomputers. If you're starting to understand why scientists have spent years trying to crack this problem, like this video right now, because the solution UChicago came up with is genuinely elegant. So how did University of Chicago researchers tackle a problem that even supercomputers struggle with? Instead of trying to model every single electron in a system individually, which is exactly the approach that sends computing demands spiraling out of control, the team found a way to swap in a much smaller, more manageable set of numbers. This set describes the possible interactions between every pair of electrons, rather than tracking each electron individually. Scientists call this a two-electron reduced density matrix, and it functions almost like a compressed map of the entire system. By measuring this reduced set of numbers, researchers can build what one of the study's authors described as a map of all the different phases a quantum system can experience. Picture it like the difference between memorizing every single turn of a cross-country road trip versus just glancing at a simplified map that still shows every major route. You lose some of the fine detail, but you keep everything you actually need to navigate, and you save an enormous amount of mental effort in the process. The truly remarkable part of this discovery is that the team tested this shortcut against the traditional, far more data-heavy method and found it was just as accurate. That's the kind of result that doesn't happen often in physics. Usually, when researchers find a faster or simpler way to do something, there's a trade-off somewhere, a bit of precision sacrificed for a bit of speed. Here, the scientists got both. They landed a dramatically simplified calculation, and one that held up just as well as the slower, more cumbersome traditional approach. According to the researchers involved, this map also comes with an unexpected bonus, letting scientists spot transitions that might otherwise slip past older methods entirely, while creating a powerful visualization that makes it far easier to grasp a high-level view of an incredibly complex quantum system. If you appreciate elegant problem solving, this is exactly the kind of moment that makes quantum physics so addictive to follow. Like and subscribe if you want more stories like this one. Now let's connect the dots, because these two discoveries on the surface look like they're solving completely different problems. One is about creating entangled quantum states using nothing more than carefully adjusted energy levels inside an optical cavity. The other is about simplifying the brutal math behind quantum phase transitions using a clever substitution trick. But both breakthroughs share the exact same underlying philosophy, and it's a philosophy that's becoming a defining trend across the entire field of quantum research right now. Instead of throwing more expensive, more complicated hardware at hard problems, researchers are increasingly finding ways to extract the essential physics while stripping away unnecessary complexity. It's almost the scientific version of working smarter instead of harder. And when a single university manages to pull this off twice in 1 month across two completely different subfields of quantum science, that's not a coincidence anyone in the field can easily brush aside. If you're starting to sense why people are calling this an unusually strong stretch for quantum research, you're following the story exactly right. It's also worth pointing out who's actually behind these discoveries, because the names involved matter here. The entangled state breakthrough came out of the lab tied to the University of Chicago's Pritzker School of Molecular Engineering, an institution that has quickly built a reputation as one of the leading hubs for quantum science in the country. In fact, the broader quantum research ecosystem at the University of Chicago has earned recognition as the top-ranked institution domestically for quantum physics research, and one of the top-ranked institutions globally. That's not a small claim. That's the kind of ranking that puts a Midwestern research university directly in the same conversation as the most famous quantum labs on the planet. The quantum phase transition shortcut, meanwhile, came from a theoretical chemist working within the university's Department of Chemistry and the James Franck Institute, alongside graduate students who spent years pushing through a problem that, by their own admission, had been historically underexplored simply because it was too difficult to model with existing tools. When you put both teams side by side, you start to see a pattern of a university that isn't just publishing papers for the sake of it, but is systematically tearing down the specific technical roadblocks that have been slowing the entire quantum computing industry. Let's talk about why any of this actually matters beyond the walls of a physics department, because that's usually the question people care about most. Quantum entanglement isn't just an academic curiosity, it's the foundation of next-generation sensors that could detect diseases earlier than ever before, secure communication networks far harder to hack than anything we use today, and the eventual quantum computers that could simulate complex chemical reactions for designing new medicines and materials. Meanwhile, understanding quantum phase transitions has historically led to some of the most important technological leaps in modern history. The same kind of foundational physics research that seemed purely theoretical decades ago eventually gave the world MRI machines and the transistors that power every computer and smartphone on the planet. So when scientists say a discovery like this could open new doors for technology, they're not exaggerating for headlines. They're pointing toward the same kind of slow foundational progress that has repeatedly turned abstract physics into life-changing everyday technology. If that kind of long game excites you as much as it excites us, make sure you're subscribed, because we cover these foundational breakthroughs long before they become mainstream news. There's also a bigger picture worth zooming out to here, because the University of Chicago isn't operating in isolation. This entire wave of progress is happening within a much larger quantum ecosystem that includes partnerships with national laboratories, federal funding through agencies like the Department of Energy, and collaborations with some of the biggest names in global technology. The university's quantum research draws support from programs specifically designed to push the boundaries of quantum information science, and it benefits from deep ties to nearby national labs that bring world-class infrastructure and expertise into the mix. This matters because breakthroughs like the two we just covered rarely happen in a vacuum. They're built on years of accumulated knowledge, shared resources, and a research culture that rewards scientists for tackling exactly the kind of stubborn, unglamorous problems that take years to crack. The fact that this particular university has become a magnet for that kind of work is exactly why it keeps producing headline after headline in a field where most institutions are lucky to make this kind of impact even once in a decade. It's also worth pausing here to address something a lot of viewers are probably already wondering. If these shortcuts are so simple, why didn't anyone find them sooner? That question actually gets at one of the most underappreciated truths in scientific research. Simplicity in physics is almost never obvious in advance. Researchers spend years building enormously complicated models because the complicated approach is usually the first one that mathematically makes sense. Finding a simpler path requires someone to step back, question every assumption baked into the existing method, and ask whether all that complexity is actually necessary in the first place. In the case of the entangled state discovery, the team had to recognize that the same outcome scientists had been chasing with elaborate hardware could be achieved through nothing more than precise energy level adjustments on equipment that already existed. In the case of the phase transition shortcut, the researchers had to realize that tracking every single electron individually was overkill, and that a smaller set of paired interactions could capture the same essential physics. Both insights sound almost obvious once someone finally explains them out loud, which is exactly why they're so easy to underestimate from the outside. Getting there in the first place is the genuinely hard part, the part that took years of failed attempts most people will never hear about. And that's exactly the kind of quiet, grinding work that rarely makes headlines until someone packages the result the right way for an audience to actually appreciate. This also raises an interesting question about how breakthroughs like these actually reach the public in the first place. Most foundational physics research, including both discoveries we've covered today, gets published quietly in peer-reviewed journals like Physical Review A, where it's read mainly by other specialists in the field. There's no press conference, no flashy product launch, no billion-dollar valuation attached to the announcement. Instead, university communications teams put together a plain language summary. A science journalist or two might pick it up, and the story circulates through science-focused outlets before slowly trickling into broader public awareness, if it ever does at all. That's part of why stories like this one are so worth covering. The actual scientific contribution can be just as significant, sometimes even more so, than the splashy commercial announcements that dominate the news cycle. But it doesn't come with the same built-in marketing machine. Somebody has to translate the dense academic language into something the average person can actually follow and appreciate, and that's exactly the gap channels like this one are trying to fill. It's also worth noting how these two discoveries fit into the University of Chicago's much longer track record in this space, because neither breakthrough came out of nowhere. The university's quantum research ecosystem spans multiple departments, including chemistry, physics, computer science, and molecular engineering, all feeding into a tightly connected network centered on the Chicago Quantum Exchange. That kind of cross-disciplinary structure matters more than people often realize. The entangled state breakthrough drew on the kind of optical physics expertise you'd expect from a molecular engineering program, while the phase transition shortcut leaned on deep theoretical chemistry knowledge, combined with mathematical tools more commonly associated with computer science and physics. When a university builds an environment where those different disciplines constantly run into each other, sharing seminars, sharing graduate students, and sharing lab space, the odds of producing exactly this kind of creative, boundary-crossing shortcut go up dramatically. It's a strong argument for why concentrated, well-funded hubs tend to outperform scattered efforts spread across many smaller, disconnected institutions. There's also a quieter, more human side to this story that's easy to overlook amid the excitement over the science itself. Behind both discoveries are graduate students who spent years working through dead ends before reaching a result worth publishing. Research like this rarely moves in a straight line. For every successful simplification that makes it into a journal, there are almost certainly months or years of failed approaches, recalculated models, and frustrating setbacks that never get mentioned in a press release. The researchers involved in the phase transition work have spoken openly about how certain areas of quantum physics remain underexplored precisely because they're so difficult to model, which is itself an admission that plenty of smart people likely tried and failed to find a shortcut like this before it finally came together. That persistence matters because it's a reminder that the clean, simple explanation you hear in a video like this one is almost always sitting on top of a much messier, more difficult process that played out behind the scenes for years before anyone outside the lab ever heard about it. It's also worth comparing this Midwestern quantum surge to what's happening at other major players around the world because context makes the achievement even more impressive. Companies like Google, IBM, and Microsoft pour enormous sums of corporate money into quantum hardware, often measured in the hundreds of millions or even billions of dollars, chasing headline-grabbing milestones like quantum supremacy. National research powerhouses in China have invested heavily in massive photonic quantum experiments designed to demonstrate computational advantages classical machines simply cannot match. Against that backdrop, a university research team working with comparatively modest federal grant funding, producing two genuinely useful theoretical shortcuts within the same 30-day stretch, represents a different kind of progress entirely. It's not about brute force spending or building the single biggest machine on the planet. It's about outthinking the problem, finding the mathematical or experimental shortcut that lets smaller, smarter teams punch well above their weight. That approach has a long and successful history in American science, and it's exactly the kind of advantage that doesn't show up in a press release about billion-dollar investments, but tends to matter just as much, if not more, over the long run. There's one more angle worth exploring before we wrap up, and it has to do with timing. Why does it matter that both of these shortcuts landed in the same calendar month, rather than spread out across a year or two? Part of the answer is simple momentum. Research groups working in adjacent fields, sharing the same university infrastructure, the same funding environment, and often the same hallway conversations at conferences and seminars, tend to feed off each other's progress in ways that aren't always obvious from the outside. A breakthrough in one corner of quantum science can shift how researchers in a completely different subfield think about their own stuck problems, even if the two results aren't directly related on paper. There's also a less glamorous explanation worth mentioning. Academic publishing has its own rhythm, with papers often appearing in clusters around journal submission deadlines, conference proceedings, and grant renewal cycles, which means breakthroughs that took years to develop can sometimes surface publicly within weeks of each other purely by coincidence of timing. Whether this particular cluster reflects genuine momentum inside the university's quantum program or simply the natural ebb and flow of academic publishing, the end result for the field is the same. Two real peer-reviewed contributions landed in the same narrow window, and together they chip away at two completely different walls standing between today's quantum experiments and tomorrow's quantum technology. So where does this leave the broader race for practical, real-world quantum computing? Despite headlines that sometimes make it sound like quantum computers are right around the corner, the honest answer from researchers themselves is that there's still a long road ahead. Even the scientists working closest to this technology openly admit that fully mature, large-scale quantum computers capable of solving everyday problems aren't yet a reality. But shortcuts like the two we just walked through are exactly how that long road gets shorter. Each simplified calculation, each clever substitution, each clever tweak to existing hardware instead of building something new from scratch, chips away at the wall of complexity standing between today's experimental quantum devices and tomorrow's practical quantum technology. Two genuine shortcuts from a single university in a single month won't single-handedly deliver a working quantum computer to your living room, but they are exactly the kind of incremental, hard-won progress that history shows eventually adds up to genuine transformation. We'll be watching closely to see what the University of Chicago's quantum researchers uncover next. Given the pace they've just shown, we don't think we'll be waiting very long. If you made it this far, you clearly care about where this technology is actually headed, rather than just the hype surrounding it. And that's exactly the kind of viewer this channel is built for. We try to dig past the press release version of every story and get into the actual mechanics of what changed and why it matters, because that's where the real long-term significance always lives. Let us know in the comments which of these two breakthroughs surprised you more, and we'll see you in the next videos.